Most of us here in this room, I think, probably grew up during the space age, as did I. And so behind me is a picture of the Earth. This is probably one of the most famous pictures from the space age. There have been many different versions of it. This is usually called the blue marble. It is a view of our world that is enabled by the fact that we have developed the ability to send spacecraft far enough away from the planet that we can turn the cameras backwards and look at the Earth and take a full picture of what it looks like from afar. There are various pictures of it with the clouds, without the clouds, from various sides. This particular picture is centered on the Middle East, which we will talk about briefly today in our discussion. The ability to see the Earth is a very powerful one. We all kind of know about the world that we live on, but the ability to see it as a single, unified, connected entity gives us a very deep sense of how interconnected we all are, and also in many ways about the fragility of the planet. And both of those things have important bearing on the discussion that we're going to have today, which is the question of whether or not there is life elsewhere in the cosmos. So this study is called astrobiology. It is a discipline in science, which as humans, we have thought about for thousands and thousands and thousands of years. But as a scientific enterprise, it's really only a few decades old. And it has certainly changed dramatically and become more prominent even during my scientific career, which has only been 20 or 30 years now. So what I'm going to tell you today, we could talk every day like this for a year and not cover everything we could possibly talk about in astrobiology. But I'm going to tell you a little bit about what we think about and why, and hopefully give you a little bit of a framework that will let you ponder these questions on your own, to give you the kind of extremes that can inform our personal philosophy and thinking about the meaningfulness of this question of whether or not we're alone in the cosmos, and hopefully give you something you and your friends can chat about when it gets to summertime and we're all hanging out around the barbecue. So let me go ahead and start by sharing some slides with you. And I think you should be able to see my screen now. So this is a picture from out west. Diane told you I'm an amateur astronomer, so lots of my amateur astronomer friends are also astrophotographers. This is a picture from a very well-known astrophotographer in the hobby of the Milky Way, which is our own home galaxy over the Grand Tetons in Wyoming. The Milky Way, for those of you who've lived in Chicago your whole life, is the diaphanous band of light that you can see formed from the light of all the stars in the Milky Way Galaxy. They are like tiny, tiny candle flames that are too far away to see individually, but when they are sending their light towards Earth together, you can see the light of them stretching across the sky. And I always love taking my colleagues and friends from the city out to do stargazing when they've never seen the Milky Way, because the first time you see it in the sky, you think it's a cloud, and it is not. It is the light of 400 billion suns slowly making its way towards Earth for us to see when we can stand out in the dark meadow. There are few experiences as powerful as standing out and seeing the universe this way. I grew up in the Rocky Mountains in Montana and Oregon and Colorado. We euphemistically call this country Big Sky Country, because when you are standing out there, the sky goes on forever, from horizon to horizon and far deeper than you can see. You get a very profound sense of how small you are when you're sitting facing the universe in this way. So let's talk about that as the beginning of our discussion, right? So this is one of the most famous pictures that we as the human race have ever taken. It was taken by our old friend, the Hubble Space Telescope. When we launched Hubble, there were certain things we wanted it to do. One of which is we wanted it to look at many places in the sky which we thought were empty, places where we had seen nothing. And we asked Hubble to go back to that point time after time after time again until it had observed and taken photographs of that point for a total of 28 days. And we took all those exposures and we stacked them together to make a single image. And this is that image. It's called the Hubble Ultra Deep Field. What's remarkable about this image is that every single fleck of light, every little bit of color, every single thing you see is a distant galaxy somewhere far away in the cosmos. Some of them look much like our home galaxy, the Milky Way. If you look at this yellow one down here on the lower left, that is a spiral galaxy that looks not unlike we think the Milky Way looks. But if you look at all of the others, you will see a remarkable diversity of different galaxies, different colors, different shapes, different sizes, all of which are indicators of the life history and the future evolutionary track that all of these galaxies have. The total size of this picture is, if you take a dime and you hold it out at arm's length, the size covered by this picture on the sky is about the size of Roosevelt's eye on that dime when you hold it stretched out away from you at arm's length. And within this single picture, there are some 5,000 individual galaxies. And so if I were to imagine the entire sky covered with little Roosevelt eyes, then there are some 500 billion galaxies throughout the entire universe. Each one of those galaxies is much like our own Milky Way galaxy. As I told you a moment ago, the Milky Way has some 400 billion stars or so. And so there are something like 100 billion trillion stars in all of the cosmos. Okay, so that's count to a trillion 100 billion times. Okay, it's an enormous number that is far outside any number that you and I may ever encounter in our normal everyday lives. One of the great discoveries of just the last couple of decades is that we long suspected, but now we know because we can see them and observe them in our telescopes, is we think every star has a family of planets, not unlike our own sun. And so if you take those 100 billion trillion stars and you multiply them all by 10-ish planets or so, there are a trillion worlds in all the cosmos. But in all of that vastness, this world, the one that you and I are sitting on right now, this is the only planet that we know with certainty that has life upon it. Okay, and that fact is the remarkable beginning of our discussion today. Everything we want to think and imagine and talk about and think about with regard to life elsewhere in the universe is completely influenced by our experiences here on this world with the only example of life we know. Diane told you at the beginning, she told you about the creation mythos and how many of them are rooted in the discussion of the primeval waters. And indeed, that's a very interesting and remarkable intuition on our part as the human species, because scientifically, one of the prejudices we have about life is that we think water is essential, because for every little bit of life we know on Earth, water is an essential part of it. Water is required for life processes. We think life began in the waters. And indeed, if something were to happen to this planet, which is 70% covered with water, then if the waters disappeared, then we certainly believe life would disappear as well. But even so, today, if you go out in your backyard, you see that Earth is a planet that is positively rippling with life. Everywhere that we go on the planet, everywhere that we look, we see life in some form. Some of it's quite familiar. Maybe it's a squirrel or a daisy or a dragonfly or your people or your pets. And others of it is less familiar. Platypuses, tardigrades, anglerfish, slime molds. But all of it just surrounds and penetrates and fills this planet in every nook and cranny. Life is prevalent and very industrious at surviving on the planet Earth right now. Our understanding of life has been growing and changing dramatically over the last, I would say, century or so. largely informed by our attempts and our desire to kind of classify and understand all the myriad different life forms that we see. And one of the things that we have discovered is that all life is on Earth is interconnected, not just in the kind of obvious ways that we live side by side here on the planet, but in the very deep ways as well. And so you will often, if you take biology, hear this described as the tree of life. This is an artist rendition of this from a very famous artist that I know named Ray Troll, who I like very much. But you see that all of the life is part of this kind of ever-branching tree. It's all connected as you go farther back towards the center to the roots and the trunk of the tree. Humans stand on one branch out here on the extreme upper right, but if you follow the branch backwards, you can find pathways between us and all of the other life on the planet. So why is this? Why have we come to this conclusion that life is all interrelated, that we're all part of the same big family? Well, this is a realization that has come from our ability to understand the macromolecular biology of organisms on the planet, that all organisms on the planet are governed, are described by a master molecule that we call DNA, deoxyribonucleic acid, for those of you who haven't been in biology in a long time. This famous double helix is the mechanism by which life encodes the genetics that then in turn describes the instructions for how to make life and how to give life the instructions for how to carry out its lifey processes. How do I turn food into energy? How do I reproduce? How do I create eyeballs and hands when I'm making a new life form, a new baby, right? All of that is encoded in this master molecule. And what's remarkable about it is that my DNA can describe how to make a human, but the DNA of an oak tree out in my yard can describe how to make an oak tree, but it's the exact same alphabet, it's the exact same language, it's the exact same mechanism by which all of that information is described. I often describe this to my students as the genetic alphabet, which is just 4 letters, which describe the different rungs that you can have there on the DNA molecule, as being letters in an alphabet that you can combine in different ways to write different books. And each book that you could write with that alphabet is the DNA description of a different life form on the planet Earth. The discovery of DNA was made by a remarkable scientist named Rosalind Franklin. She was an expert at taking pictures of the microscopic world using a technique called X-ray crystallography. This is her very famous picture, the very first picture ever taken of DNA. You can see that kind of X shape in the middle there is the double helix and the rungs on the DNA ladder. This was a picture she took with her graduate student, Raymond Gosling, and is now part of the history of how we discovered the genetic code and the remarkable relationship that all life on Earth shares. So let's take this as our starting point, the Earth and our understanding that all life is interconnected and that it's the only planet that we know with life. And I'm gonna give you 2 quotes, one right now and one at the end, which kind of say exactly the same thing, but they say it with profoundly different mental attitudes about the prospects of life here on Earth and life elsewhere. So I'm going to start with the famous science fiction author, Arthur C. Clarke, who said there are 2 possibilities in answer to the question of whether or not life exists elsewhere. 2 possibilities exist. Either we're alone in the universe or we are not. And both are equally terrifying. Okay, and I've added that emphasis there because I think that's the interesting difference between this and the quote I'll show you at the end. So this is the framework that people often approach the question, the philosophical question, the ethical questions about trying to understand the nature of life elsewhere in the universe. If we are the only life in the universe, then what happens to us and this planet? It would be a remarkable tragedy if we somehow vanished, if there is no life elsewhere. But if we are just one of many examples of life, then I think for humans, who I think very often regard ourselves as the apex species on the planet, it could have profound cultural, philosophical, psychological consequences on us as a species. Okay, so this is Clark's kind of capturing of those two extremes. And so I want you to keep this in mind as we talk through this here. And then I'll come to another version of this quote at the end, which I think I like a little bit better because it agrees more personally with my my philosophy. I'm not really scared by either of these possibilities. So, well, that's not true. I am, but we'll talk about that later. So, okay. So what are the kind of extremes? So even if you're not a scientist like I am, and you've never thought about this, I think it's not uncommon for people to have thought about the question of whether or not Earth is the only place there is life in the cosmos. You stand out and you look at the night sky, it's kind of just one of those questions that pops into your head. Are we part of something bigger than we are? If you watch a lot of science fiction is replete with life elsewhere in the galaxy. And you may have asked yourself, is that true or not? Is there life elsewhere? So even if you're not a scientist, you may have thought about this. So I want to give you the kind of extremes that we as astrobiologists think about. So the first is there's a group of us who believe life must in fact be common in the universe, okay? We often call this the principle of mediocrity. It is a natural extension of the scientific idea of Copernicanism, that there is nothing special about the Earth. And because there's nothing special about the Earth, it's just like any other planet or any other corner of the cosmos, the fact that life arose here is suggestive that there's no reason why it couldn't have arose somewhere else. Okay, there's nothing special at us. That's what we mean by the principle of mediocrity. The other extreme is something is a viewpoint where we think life must be rare. Okay, and this is often called the rare Earth hypothesis. And in this case, we look at the very complex machinery of life here on Earth. Even though life is remarkably common, it's all shares this common molecular machinery that you and I were talking about. And the chemistry and the genetic code and the way the instruction set turns itself into all the different forms and structures and operations that life engages in is something that over time had to slowly evolve and be selected for the things that we see going on and being used by life today. And that process, scientifically, we believe is a random process. It's driven by environment, it's driven by chance errors in the genetic code, and then it's driven by whether or not the life actually survives after the changes are made. And so people often look at that and they're like, wow, that's so lucky that it all happened. It must not be able to happen very often. And in that case, people believe life must be rare. And so in fact, we call this the rare Earth hypothesis. Earth is just one example of how incredibly lucky life is to have survived and grown here. And then I think for many of us, there is this place in the middle. Maybe there's life, maybe there's not. We don't know enough about any of this. We can talk about it scientifically, we can speculate, we can tell you why we believe one thing or the other, but we don't have strong reasons necessarily to believe in the principle of mediocrity or the rare Earth hypothesis. And so when I talk about this in my class, I usually call this the principle of indecision. And as scientists, right, this is a great place to be. We shouldn't necessarily give in to our biases, our prejudices that we bring to the table based on our life experiences and our scientific experiences. We should always just let the universe guide us to what the answer really is. Okay, so I usually call this the principle of indecision, where I could imagine either one of these possibilities might be true. And so I want to use this kind of framework for us to discuss the question of whether or not we think there's life elsewhere in the cosmos. Okay. Now, we could go on at great length about any topic related to astrobiology, but I think what I'm going to do here, just for the second half of this chat, is I'm going to give you a framework that I like very much for thinking about this question and answering the question posited by these three boxes. For those of you who have not been in science class for a long time, I don't want you to feel too much anxiety, but this framework, I think, is useful if you were to write it down on your own to kind of explore what the possible outcomes and the possible implications of the things we know about the universe are. And the reason I say I don't want you to have any anxiety is because I'm going to walk you through doing a little bit of math. Okay, and I know a lot of people are like, no, I quit going to school because I don't want to do math anymore. But it's okay, right? All you have to do is multiply. And I think all of us remember how to multiply. So I'm going to give you some multiplication to do. I'll do some examples of it to show you how it fits into the framework we're looking at right now. And if you want to do some more on your own, then you can write it in the back of your journal and go try and do it. Okay? So this little bit of math begins with this gentleman. So this is Frank Drake. Frank is one of the grand old astronomers in our field. Frank is 92 now, I think. He's now retired, but he is really the person who started the scientific thinking of astrobiology, to my mind. He is the very first person to imagine what it would take for interstellar civilizations that are spread across the galaxy to communicate with each other. So he is pictured here. So he was born in Illinois and got his degree at Urbana and then at Harvard. But his first job was at the National Radio Astronomy Observatory. So this is in West Virginia. This was the telescope that was there when he arrived. It's the 85-foot telescope. It was later part of a big instrument there called the Green Bank Interferometer. And the interferometer is not working anymore, but the telescope's still there. You can see it. And in the 1950s, Frank used this telescope in a project called Project Ozma, where he looked through the sky trying to detect radio signals from an extraterrestrial civilization. Radio signals that they may have tried to send out to the universe, pinging the worlds around them to say, we're here, is anybody out there? And that's an activity that we as humans have also engaged in. And I can tell you about that sometime if you want to know about it. After Project Ozma, Frank did not detect any signals, and I think most of us know that we have not detected any signals from outer space that we believe are signals from alien civilizations. But Frank decided to have a conference there at Green Bank about the question of whether or not there's life in the universe. And so he invited lots of his scientific colleagues to come to talk about all of the little specific things in science that we have to think about that would influence the answer to this question. Could there be life elsewhere in the universe? And could we communicate with that life? And so he set up a series of talks, and what he realized is that each one of those talks could be boiled down to a single number that tells us something that we think about the universe. And he realized that if you take those numbers, there's 7 of them, and you multiply them together, that those numbers combine to give you the number of alien civilizations in the Milky Way Galaxy with whom we might be able to communicate. Okay, so that equation today is called the Drake equation. Okay, named after Frank. If you go to the Green Bank Observatory, there's a conference room where they had the conference, and there's a plaque on the wall with the Drake equation. It's become so important and so influential in our thinking about astrobiology. Okay, so let me show you the equation, and what I'm going to do is I'm going to talk you through all of the numbers in it and what the values of the numbers might be. And before we finish today, we're going to predict how many civilizations there may be in the Milky Way Galaxy. Okay, so this is the Drake equation. Okay, it's 7 numbers. They have kind of funny symbols to remind us of what they are, but we're always trying to get to what's over here on the left, n, the number of civilizations in the galaxy. And then over here on the right, we have to, from our understanding of the universe, determine what each of these 7 numbers are. So let me walk you through those 7 numbers, and then we'll multiply them all together. So the first 3 numbers are all about astrophysics, okay? And I will tell you that in my career in the last 20 years, these numbers have changed, but they are becoming more and more stable. We are more and more confident that we know what the values of these numbers are. The first number over here on the left is called R star. Stars, like humans, are born, they live their lives, and in the end, they perish. So R star is our estimate of how many stars are born in the Milky Way Galaxy every year. Stars condense out of gas and dust, nebulas in the sky. They form very brilliant clusters of stars that we call open clusters. They look like smatterings of jewels on this background canvas of gas and dust. And then they slowly blow all this dust away, and then they move into the galaxy and become stars like our own sun. Okay, so all these stars that form, there are about 6 that form every year in the Milky Way. This middle number is a number that we had no idea what it was when I became an astronomer 20 years ago. It's the fraction of stars in the galaxy that have planets around them. Okay, so it's a number between 0 and 1. Now, we've always suspected that this number is not 0, but when I got my PhD, we had not yet ever seen stars with planets other than the sun. Okay, we write about it in science fiction all the time. Star Wars and Star Trek totally tell us there's planets around other stars, but we had never, with telescopes and scientific instruments, been able to detect planets around other stars. Today, that is not the case. We have detected some 5,000 individual planets around other stars. Did I look up the number before? I did not look up the number today. That number changes every single day because we are adding planets at a prodigious rate. But today, I think if you ask most astronomers, they will tell you this fraction should be close to 1. Virtually every planet, every star should have planets around it. Now, in the interest of not overestimating the number of worlds and life forms out in the universe, I'm going to be conservative today. I'm going to take this number to be 1/2. But I would bet you a bag of jelly donuts that most of my colleagues will tell you this number is too low. Okay, it should be closer to 1. This last number is related to our prejudice that I told you about earlier, namely that we think water is an essential bit of environment necessary for life. So this number is the number of habitable worlds around a star that has planets. Now, the notation here, NE, we used to say number of Earth-like worlds. We're trying not to say Earth-like anymore. So what we really try and say is habitable. And what we mean is the world at an appropriate distance from its parent star, that the temperature is warm enough to melt ice and keep water liquid, but it's not so hot that the temperature from the star boils the water away. So in our own solar system, there are actually 3 worlds that sit in this so-called habitable zone: Venus, Earth, and Mars. And those of you who remember your basic astronomy will know that Venus has a runaway greenhouse effect. So it's super, super hot. So there is no liquid water on Venus. Mars has lost lots of its atmosphere during its life. Its gravity is much lower than Earth, and so it has lost a lot of its water, but much of the water on Mars is bound up in its ice caps and in its permafrost layer. And one of our kind of key things that we do right now with our missions is we're looking for evidence that there is liquid water in places on Mars still. And we see evidence that it is true, possibly subsurface. Okay, so for this number, we could pick any number we wanted, but based on our experiences in our own solar system, I'm going to take that number to be 2. Okay, it could be 3, it could be 1, but let's take it to be 2 because of Mars. Okay, so if I multiply these 3 numbers together, these first 3 numbers in the Drake equation give us the number 6. Okay, so just keep that, and then we'll come back to it. Okay, so the last 4 numbers are much more poorly understood. And that's because the last 4 numbers are the numbers that capture what we think about life itself. And despite the fact that you and I, if we go out and we look around us, we see life everywhere, we don't know a lot about the origins of life, about how life gets started. We know a little bit about how it changes, but we don't know how rapidly or how often it can change in the face of necessity. So there's a lot of uncertainty about life itself. And so these numbers are the numbers that people will argue about a lot more if they talk about this. The first number is what fraction of planets actually have life on them. Okay, so we don't know the answer to this, even in our own solar system. I'm going to use the word planet broadly here to mean any planetary sized object that is round, has gravity, and could possibly support life. So within our solar system, that could include the moons of Jupiter and Saturn. It could include any number of worlds in the asteroid belt. It could include any number of worlds out in the region where Pluto lives. There are about some 150 objects that we might call planets. And in all of those, Earth is the only one that we know with certainty that has life on it. So for the sake of being conservative, there may be life elsewhere in the solar system, but because of what we know, let's just take this number to be 1 in 100, because that's based on our data that we have at our disposal. The second number is if you take that pile of planets that you think have life on them, you can ask, of those planets that have life on them, what fraction of them have intelligent life? And this people will argue about for days and days on end. It often starts with, are humans intelligent or not? That's a good question to answer. But I show here a chipmunk, right? Is a chipmunk intelligent? Well, in the context that we're talking about, maybe, maybe not. But they're smart, right? They raid my bird feeder, they take all the peanuts out of them, and they store them away in their warrens so that they have something to eat over the winter. That seems pretty smart, right? That's a little bit of intelligence. There are things that we would think are not intelligence. The grass there in the background. Grass doesn't respond the same way a chipmunk does, but it's smart enough to know to send its roots down and to grow upwards towards the sky. Is that response to environmental stimulus, or is it intelligence, right? The crux of this discussion revolves around not the obvious cases. I think people obviously, maybe, I shouldn't speak for all my colleagues, but in general, I would say most people would regard grass as not being intelligent in the way that we mean when we say intelligence. But when you look at our fellow life forms in the animal kingdom, birds, the chimpanzees, the whales, chipmunks, right? There are all kinds of life forms that exhibit what you and I would regard as intelligence. Okay, so again, in the guise of being conservative, let's take this number to be 1/100th as well. Now, Frank was interested in communicating, and so he also asked, what fraction of civilizations become communicative? And what he meant by that is what fraction of civilizations develop the technology by which they could send and receive radio signals. Now, despite the fact that there are lots and lots and lots and lots of intelligent life forms on the planet, we, the human species, are the only ones that we know of that have developed this kind of technology. The chimpanzees don't have it, the dolphins don't have it, ravens don't have it, but humans have. So again, we're going to take this fraction to be a very small number. There's probably way more than 100 intelligent species on the planet Earth. So this may be an overestimate, but by and large, let's just take, of all those intelligent life-bearing planets, let's take the fraction that develop radio technology to be 1 in 100. Okay? So those are the kind of big ones about life that people argue about. You can imagine what the difficulties in having those discussions are. But the big one, the one that causes the most consternation, is this one, L. How long does a civilization live once it's there? Okay, civilizations live and die by many means. Sometimes they perish by natural causes. Sometimes they perish by their own actions. And we know no example, although perhaps we are example, they could also survive indefinitely. Okay, but you have to put a number here for how long they did survive. And people's own personal reflections on our species in particular is often what informs the number that they use for the lifetime of a civilization. If you're like me, you grew up in the Cold War. There is a group of my astrobiology friends who think that once you enter the atomic era, the lifetime of your civilization could be very, very tiny. Either by deliberate action or by accident. There have been many close calls in the atomic era where we could have abruptly destroyed ourselves. And so there are astrobiologists who think the lifetime of a civilization should be 100 years, because from the development of atomic theory to the development of atomic weapons, that's how long it took us to arrive at a point where we could have utterly destroyed the planet. Those of us who think about science today are more concerned with other existential issues like climate change. Climate change is being driven by human activity, and it is changing the planet rapidly, which will have profound effect not just on our civilization, but on the life forms we share with the planet. And we don't know how long this will take to change, to bend the curve, whether or not there is an unstoppable point we may reach and fall over the edge of, or what, okay? But this number here would profoundly influence the length of time for our civilization. But we are here, and we know we have been here for some time. So the oldest human civilization of which we have archaeological records is the Indus Valley civilization around the Indus River in the sub-Asian continent near India. The Indus Valley civilization started about 7,000 BCE and was kind of really prominent and strong about 5,000 BCE. It vanished ultimately by changing climate and drought in the Indus Valley area, but the peoples of the Indus Valley civilization eventually were absorbed and became parts of the civilizations around them. And so one number we could take for human civilization is our historical record. So we could take something like 5,000 years. So rather than being overtly negative or overtly optimistic, let's take the historical record of 5,000 years and compute now, this is the last number we need, what the number of civilizations in the galaxy is, okay? So if I take all those numbers and I get my calculator out, there's the 6 from the astrophysics at the beginning. I can put in all the numbers you and I just discussed and multiply them together. And the number of communicable civilizations in the Milky Way is 0.03, a number less than 1. We could be the only civilization in all the 400 billion stars in the Milky Way Galaxy. We could be very, very alone. Okay? Now, if you're staring at that, you should be like, yeah, but wait, the dinosaurs, they didn't have a civilization like you and I have, but they lived on the Earth for 170 million years. So if I go back to the Drake equation and I change L from 5,000 to 170 million, I get that there could be 1,000 civilizations strewn throughout the Milky Way Galaxy, all of them looking skyward, much as we are, wondering if they're the only civilization out there or not. But there's one little bit of this that I want you to think about, and then we'll end. Okay, we're talking about in the Drake equation, the way I just told you about civilizations that we could talk to. Is there someone that we could send a selfie to and say, look, this is what humans look like, send us one back, okay? But if talking in social media with alien civilizations is overrated, if all we really care about is there life elsewhere, not is there intelligent life that I can talk to, is there just life of some sort, we can also use the Drake equation to calculate that. I just go back to the Drake equation and I delete those two numbers that have to do with intelligence and communication. With just these 5 numbers, and you can go back and use the same values we used before, with just these 5 numbers, the Drake equation tells you how many worlds are there that has life at least as complicated as dinosaurs. If I put the number for the dinosaur civilization there for L, 170 million years. And if I do that, there could be 10 million planets in the Milky Way Galaxy that has remarkable complex life forms that you and I would recognize as being alive. Dinosaurs and trees and flowers and plants and pterodactyls and all of those sorts of things that you and I recognize as life, not the life we see today, but as things that are definitely complex and alive. The galaxy itself could be rippling with complex life, just maybe not life that we could communicate with. Okay? So I promised you I would end with the other quote, and this one's from Buckminster Fuller. So Buckminster Fuller said, "Sometimes I think we're alone," that first number that we got. He said, "Sometimes I think we're not. And in either case, the thought is staggering." The idea that we could be alone is very humbling and makes you feel very small. The idea that you could be just one example in a cacophony of planets that has life on them can be very uplifting and enlightening, that we are part of a much bigger thing than we are just here on the Earth. But I think ultimately, because we do have our intellect, we do have our ethics, we do have our philosophy to think about, ultimately, I think whatever the answer to either one of these possibilities is, the question we have to always ask ourselves is that if we are the example of life on Earth, if we're the only life, how do we answer for ourselves and our actions here on this planet? And if we are part of a much larger cosmic community, how also do we answer for ourselves and be something, be part of something bigger than we are? Okay, so I know I ran a little bit long there. I'm sorry about that. I will end there and say thank you all so much for your time, and I will hand it back to Diane.
Thank you, Shane. At this time, I'm going to invite questions, but I have rules for the questions. First is the question has to be one sentence. Try for about 15 words. And I also, as the moderator, will reserve the right to intervene or interrupt if you ask a second question or too complex a question. So I will start out, and please raise your hand so I can see if you have a question. I will start with a question, Shane. In the beginning, you talked about how many other galaxies there were. So you did all of your calculations based on the Milky Way Galaxy.
Yep.
I would assume those numbers increase astronomically when we start thinking about multiplying it by other galaxies. At least I think that's how the concept would work.
No, I think
my
that's
rudimentary math.
Yeah, no, that's exactly right. So the calculation that I just did for you with the Drake equation is for a single galaxy, because it's the only one where things are close enough that we can imagine being able to communicate, discover, observe, all of those things. All the other galaxies in the universe are so impossibly far away that with our technology today and with any technology in the foreseeable future, we don't think we're going to have the ability to see indicators of life, to communicate with possible life there, or even actually go there and visit. So you are right. Every galaxy we could do this exact same calculation for, and every galaxy may be very similar to the Milky Way. That's not unreasonable. And so each of these numbers could just be multiplied up for the entire universe. But for the places that we have some hope of answering this question, we confine our attention to our own galaxy. Okay, that's a good question.
All right, so Michelle, I see that your hand is up. Would you like to ask a question?
Yes, you mentioned that, thank you for your presentation, always
Thanks,
learn
Michelle.
something. You mentioned that there are 6 stars that perish a year. How many are born? If you mentioned that, I forgot to.
No, yeah, that's right. Yeah, no, that's actually the number of stars that are born every year.
Oh,
right?
born.
So there's
okay.
6 stars that are born every year. Stellar death is more complicated than stellar birth. And that's because stars die in different ways depending on how big they are. So stars like our sun, they will die by swelling up and getting really big. They become something called a red giant. So they swell up in their old age, and then they shrink down to a cinder that's about the size of the Earth. That's called a white dwarf. And that process is not spectacular. It takes about 10 billion years from the time the sun's born to the time the sun will become a white dwarf. And there are lots of white dwarfs. There are some in the Milky Way Galaxy. There are something like 100 million white dwarfs from stars that have gone through that process already. Much bigger stars will also swell up to red giants, but then they collapse and explode in something called a supernova. And that's supposed to happen about once every 50 or every 100 years in a galaxy like the Milky Way. But there hasn't been one in the Milky Way in about 400 years.
So stars are being born at a more rapid rate than they're dying.
Yeah, and that's because they're born with different sizes and their size that they're born at influences how rapidly they die. If they're big, they die rapidly. If they're small, they live for a long time. So
thank you.
Okay, I see a question from Benjamin F. in the chat. What do you make of the fact that life started on Earth in only one way, carbon-based, DNA-based? We don't see any other type of life that developed independently or differently.
Yeah, so that's a great question. I would answer that question in the following way, that as a scientist, what I would say is we don't know of any life that is not carbon-based. If you haunt the journals in astrobiology, you will see all kinds of discussion of what chemistry we could do other than carbon. And in fact, just, what was it? 5 years or so ago, they had detected a process in Mono Lake in California. So Mono Lake is a very mineral-rich water lake in California, and I can't remember all the details yet right now off the top of my head. But they had detected a molecular substance that they thought could be an indicator of life that went along a different path than carbon. And I can't remember what that was off the top of my head. I should know that, and I don't. But if you Google Mono Lake astrobiology possible life, you'll find a lot of discussion of that. I think we now believe it is geologic process, but the simple fact of the matter is we don't know everything, even about life on this planet. And so as a scientist, I'm not willing to rule out, to preclude the possibility that there is other pathways for life beyond carbon, even here on Earth. So.
Thank you, Shane. I see that Bob DWyer has his hand up. Bob, would you like to ask a question?
Yes, Diane. First of all, let me say that was a wonderful presentation, and I really appreciate your putting it together.
Thanks, Bob.
My question, bring it a little closer to home in our solar system. Could you share a little bit of the latest thoughts of why we think there might be simple life, not complex life, but simple life in the subsurface oceans of the moon of Saturn called Enceladus and the moon of Jupiter called Europa?
Yeah, that's a great question, Bob. So let's start with why Enceladus and why Europa. There are other places where you will hear these very similar discussions, and the reason has to do with our prejudice for the idea that life requires water. So Europa and Enceladus are both close enough to their parent planets that there are mechanisms by which the interiors of those moons are heated, which keep the water in their cores liquid. So Europa in particular has, if you look at the Voyager pictures, has the very thick surface layer of ice that we think is liquid beneath. We're thinking about missions that would drill through the ice and let a submarine go in the waters down below to look for life. And then in Enceladus, we actually see volcanic activity, what we call cryovolcanoes, which is also an indicator that there is geologic processes warming them at their core. So it's our prejudice that water is a necessity for life that's causing us to think about Enceladus and Europa. The beginning of your question, though, is why simple life forms, has largely to do with our experiences watching life forms here on the planet Earth. One of the things that has changed just in the last 20, 30 years is the recognition that life is tremendously adaptable to really, really harsh environments, particularly in the case of bacteria, because they evolve and change so rapidly compared to their environment. So the classic example that you do in biology class is you grow some bacteria on a plate and you put some antibiotic in the middle. And if you wait long enough, the bacteria change and evolve to the point where they can overcome the antibiotic. Okay, so this is the root of antibiotic resistance that we worry about so much. But in the natural environment, there are more bacteria out there than you and I or any scientist on the planet has ever categorized. The bacteria change and they are everywhere. They're in the ground, they're in the rocks, they're in the ice, they're in geothermal vents in the ocean, right? It develops everywhere. And so the notion is because microbes are so capable of changing rapidly to drastically difficult environments, that if we are going to find life out in the solar system, we're definitely going to find bacterial life.